network class. First, take a look at the constructor for the whole network. Can you guys guess what X is?
Input.
X is the training data,
Yep.
right? Which in our case will be 1000 by 28 by 28, or later on we'll convert it to 784. Right? Okay. Anyway, Y is the expected outputs. Expected outputs in our case are 10,000 because we are testing it on the entire. So anyway, sorry, my mistake. Expected outputs will still be 1000 because for 1000 inputs you have 1000, but it will be a 10 by 1 vector. One of the lines will be 1 corresponding to whatever digit is being recognized. Okay. Don't worry about the dropout. Activation function is
the type that we select.
The type that we select in all neurons except the last layer. Okay. Then the last layer activation function, I made it a separate parameter. So this way we can decide whether we need to put sigmoid in the last layer or softmax in the last layer. Okay, anyway, the rest of it is not too bad. Okay, so then as you can see, it contains a list of layers, just like I put a comment over here. Okay, then we loop through this list of layers. We create each layer because somebody will give us this list as something like this. If they want to create a network with 100 in the first layer, 10 in the second layer, they'll give it to us, right? Or if they wanted to create a 3-layer network, they will pass it to us a list like this, okay? So this num layers over here will be a list basically. Okay, anyway, so basically I equal to 0 is our first layer. So we call the constructor, we give it whatever inputs, shape, and so on. Okay, I mean the number of neurons and so on. Anyway, so this creates all the layers. Okay. The last layer, the reason we need to distinguish is because in the last layer we may decide to put a softmax function. Okay, then the next thing is the evaluate. How do we evaluate this whole network? We start by feeding the input to the first layer. The output of the first layer will be then fed to the remaining layers. Okay, and as you can see, self.layers of i-1 dot a is the actual output. Okay, so this is how the whole network will produce the output. And lastly, the train method, which is the same double loop as you guys have seen, with a slight twist on it so that we can take care of batch, mini batch, and so on. And also we can take care of the activation function. So anyway, if you go through it, you'll see it's pretty easy. So now the benefit is we can create any size network very easily. So let me show you the test code. Okay, for example, take a look at this part. If I wanted to create a network with 50 neurons in the hidden layer, 10 neurons in the last layer, then I'll call the constructor train x, train y is the same data that you're using in your current assignment, meaning 1000 by 784 by 1, 1000 by 10 by 1, right? Okay, num layers is this one. Okay, this is the dropout, which I'll talk about in a few minutes. Activation type sigmoid will be applied where? Only on the first one, not the last one, right? Then I have one more activation for the last layer.
That is
okay. So then once the network is created, then we just call the train method. Hopefully you can easily guess what is 30. Epochs.
learning rate.
Learning rate.
And what is that point?
Okay, so this is another regularization parameter, which I'll talk about in a second. Okay, so anyway, we can put, we can put stochastic, we can pick mini batch, and we can pick batch over here. Okay, so this is also an enumeration. Very quickly, let me show you this enumeration. Okay, so batch, mini batch. So then you can decide when to update the gradients and so on. Okay, anyway. So this will do the training for 30 epochs and so on, right? Okay, so very briefly, if you take a look at, I was creating 50 neurons in the hidden layer and 10 neurons over here, correct? And what's the activation of over here?
Sigmoid.
What's the activation here? Sigmoid, right? And I'm not running it too long, just for 30 epochs. So if I very quickly run it to you. Okay, don't worry about this part. Anyway, so we'll run through, hopefully quickly we can see the accuracy. Okay, so it came out to something
0.894.
0.894. Okay, if I now switch it to softmax in the last layer, and this is what you guys will do as you implement your version or modify this version.
It will improve.
Okay, so you can see 0.9024, right? So softmax, even though it previously was without softmax,
0.8924.
it was
0.8.
it was 0.894, I think, something like that. So, a little better. But like I said, depending on the data set, how much training do we have available, this will turn out to be different. Okay. Anyway, so now let me talk about regularization, and then I'll explain the dropout and so on. Okay, so one of the issues that we run into with deep networks especially is the overfitting of data. So first let me briefly explain how overfitting occurs. And then obviously we'll take a look at what are the techniques to minimize the overfitting of data. Okay, so let's say you were given some data, right? Something like this. Okay, so if you created some kind of, to make it easier, let's talk about regression and not classification. So if let's say we only use 2 neurons in the hidden layer, okay, and if we trained it, it might come up with some kind of fitting of the data according to this type of curve, right? Okay, if we made it, let's say 5 neurons over here. So then what we'll try to do is, it will try to accommodate each data because now it can do more curves. So even though our loss will be less compared to the 2 neurons, it is possible that this is overfitting the data, meaning because of our measurement error, these things were appearing over here. In reality, they should be really on this line, okay? So same way, if we made it 100 neurons, right? What it will try to do is it will use a different color. It will try to basically accommodate everybody. Okay, and you'll say, wow, I get a loss of 0 as I train it. So this must be really good. But once you give it unknown data, right? So here's an unknown data, here's an unknown data. Let's pretend here's an unknown data. Okay, it will do a terrible job on it because now it was thinking, you know, it's like a very too many peaks and valleys over here, so will not do as good of a job. So the whole idea of training a network is we want to pick a model so that it's not too complex and it's not too weak. See, correspondingly, for the same data, if you just picked a single neuron, as we had discussed, what does single neuron do?
Or linear function.
It's like a linear function, right? So it might come up with something like this, as close as you know, with sufficient training. So obviously that's terrible too. So we have to. So the goal is basically pick a model. Okay, by model we basically means number of neurons in hidden layer. If we are creating, let's say, a simple one hidden layer network, or if there are multiple hidden layers, you know, pick number of neurons in hidden layers, such that it's not too complex for the type of problem we are given, and it's not too weak for the type of problem we are given. If it is too weak, then we call it underfitting. If the model is too weak, if the model is too complex, it will do overfitting. Okay, so how do we know how to pick? See, one option, and that's why I have you try, even though I didn't pick a good example because you were really not able to see the difference between, you know, maybe a small difference, but not significant enough. But anyway, so one possibility for picking a proper model so that it doesn't do underfitting, doesn't do overfitting is just experiment, okay? Typically what we do is we have our training data. Okay, we also have our test data. So one simple approach is like you guys did in the previous assignment. We had 1,000 over here, we had 10,000 over here. So train it, then test it, because it has never seen these digits. So only if it is a good model, it will do a good job on the testing, otherwise it will do a poor job. Meaning, what I'm trying to say is don't go by the loss and saying, oh, my loss, if I use 300 neurons, my loss was 0.05. But if I use only 50 neurons, my loss was 2.98. That's not a good indicator. The good indicator is really, how does it do on the test, independent of what loss you're getting, right? Okay, so let me also mention, okay, too much training can also cause overfitting. So, you know, some of you were running it for 100 epochs, 200 epochs, and you might say, oh, the loss is going down as we train more, right? But if you keep going it for 1,000 epochs, you'll actually end up overfitting the model. Okay, so that's not good either. So let's talk about how do we determine that how many epochs to use. So first let's try to answer that. because like I said, if we use too many epochs, we will end up overfitting again, right? Which means we will not do as good of a job as on the test day. So again, there are some simple techniques, some more complex technique. For right now, if we can just understand one simple technique. So what we do is we create a training set. We create a validation set. And we have a test set. Okay, so typically 20% of the training data. And again, there's no hard and fast rule. You can use 30%, 25%, but typically 20% of the training data will be used as a validation data. Okay, so 80% will be of the training data that was given to you. You'll use it for training, but not. So in our example, how many training images did we have?
1,000.
1,000, right? So what we'll do is we'll train on 800.
Oh, so 80%.
Okay, then validation will be done on how many?
20,000, so 200.
200. Okay, so basically what you'll do is every epoch you will test it on the validation set. Okay, and see how the accuracy is improving. So if you did the validation accuracy, okay, it will come out to be something like this. The accuracy in the beginning will be low, right? So this is epochs. So it will basically even start to go down over here. Okay, so as you can, from here, you can sort of see, maybe after 70 epochs, it was really not improving. Then if we kept training more, it actually started to decrease. So that will give you an idea that after 70 epochs, it starts to saturate, okay? So anyway, that's based on the training data given to you, you can decide how many epochs to run. Okay, so now let's talk about reducing overfitting in general, and I'll show you a few techniques. Okay, so reducing overfitting, okay, from training point of view. Maybe I should say, all right, let's just take a look at it from this point of view. Okay, so there are a couple of techniques, or maybe instead of training, let me put it model point of view. Meaning, how many neurons should we pick such that it doesn't overfit? So, okay, suppose, let me give you an example. Suppose you picked 100 neurons in the hidden layer. And we'll go to our example of 10 neurons over here, right, and the input data. Okay, and let's pretend 100 is actually too complex. Okay, it should really be 70. Okay, if somehow we can go and make those weights, sum of the weights 0. So sum of the weights, if they can be made very close to 0, right? Meaning we leave it 100 neurons, but we make the training such that some of the weights automatically become close to 0, so that effectively it is the equivalent of as if it's using 70 neurons. Okay, so So if we use the weight approach, and by the way, reducing overfitting, the terminology is called regularization. Okay, so basically one regularization technique is called weight decay or L2 regularization. It's very simple. Let me show you the concept. Okay, if you take a look at our neural network, right? As we go through our, for I equal to 0 to number of epochs as an example, and then for j equal to whatever training set, and regardless you're using batch or not, okay. Anyway, as we keep going through these loops, what's our goal over here? To minimize what?
The weight.
What are we trying to minimize as we train?
The loss and
Yeah, right, you lost.
Minimize the loss function, right? Okay, so if we take a look at the equation for the loss function, right? And by the way, this loss function or also is referred to the error or the cost. Okay, some of the terminologies use the letter J, as we saw in one of the previous lectures. So basically what we are trying to do is we are trying to minimize J theta, right? With respect to what? With respect to basically theta, okay, which will be basically weights and biases. Do you guys agree? Okay. So anyway, over here, if we are using, for example, L2 regularization, this would be basically sum over whatever our training data is, y of I minus the actual, right? A of I squared. Okay, so then further, theta would be weights and biases. You'll further go take the derivative and so on, apply the chain rule. So normally this is what we are trying to minimize. We're trying to determine theta, which determine, so basically our optimization is determine theta. That minimizes J of theta, right? And how do we do that? By taking the derivative over here with respect to theta, then updating the W's and the B's, and we are able to do that, right? Okay, anyway. But like I said, if the model is too complex, even though we are optimizing, this will end up overfitting, right? So what if we do this, add another part over here by lambda W squared, okay? So these are the weights basically. Okay, so meaning in the J of theta, our cost function is defined like this. So this is our loss function or the cost function before taking the derivative. Okay, so as we minimize it, as you can see from this expression, what is it? As it's learning theta, what will it try to do? It will try to make the difference between the actual minus the expected, right? So that it starts to predict more and more correctly. Okay, for this to become low, what should be this? High value or a low value?
Low value.
Low value. So as you can see, it is automatically forcing it to choose those weights which have as low of a value as possible. Okay. Now from a gradient point of view, Okay, if you take a look at the gradient, partial j of theta with respect to partial of theta, right? Okay, so remember then this will go, the chain rule, whatever, up to the theta. Theta would be W1 or W2 or whatever, right? But what will happen to this term over here? Let me put 0.5 over here. So if I'm taking the derivative with respect to W, because the gradient of weights have to be computed, right? What will happen to this term over here? No, it will become, sorry, 2 and 0.5 cancels.
Lambda.
Do you agree? Will become
Lambda W.
lambda W, right? Okay, so now let me show you how we will incorporate this in our code. So automatically this will try to do two things: make all the weights as small as possible. Okay. Also, some of them it may even make them close to zero, so that the model is not overfitting the data. Okay. So let me erase this and show you in code now.
Professor, when do we know we have to use this error function or a cross entropy error function?
No, this has only to do with regularization. This will be whatever. So even if this was cross entropy, that will stay over here. You'll add this term to it.
Will there be a difference in accuracy if I use cross entropy instead of this one?
No, that depends on, especially if you have a multi-class problem, you should use cross entropy. Okay. But like I said, regardless whether it's a least square error or cross entropy, this will get replaced. But this still stays there. So if you do a gradient with respect to W, what I'm trying to say is this is the extra term that will get added. Okay.
This W is like what's the weight?
Weights.
We take the relative of each weight because we have like W1, W2 till W.
All of them. Because remember, if you have, let's say, 4 weights, you'll be computing partial L over partial W1, comma, partial L over partial W2. Then once you have computed this, you will do W1 minus the learning rate times the gradient, right? Same thing for W2. So this W that I put in over here is in general, doesn't matter any weight. So it only applies to weights, not to the biases. Okay, so now let me show you the effect of the regularization. Hopefully will kick in soon. Okay, so if I go to, remember the train method as I mentioned, I had put it in the network class. Okay, so if you take a look here, I wrote a method after we have computed the gradients that we will update them, regardless it's after every training data or after a mini batch or after a batch. Okay, so anyway, for example, take a look over here. How will we update the weights of a layer? Layers of whatever that layer is, ln will vary on all the layers, right? W minus the learning rate times 1 over batch size. Does that make sense? If the batch size is 10, we divide by 10 because we accumulate for 10, right?
Into the
Okay. Okay. So that was basically the gradient. Okay. So we multiply 1 over batch size learning rate times the gradients, right? Okay, but take a look at this extra term now. Okay, so why are we adding this? Remember we computed the derivative of the lambda w squared to be what?
Lambda.
We had a 0.5 in our cost function, right? So it's lambda w.
Yep.
So take a look. So lambda, for example, could be 0.01 or could be 0.1. So somebody will decide. So essentially, by simply adding the weight update to lambda times w, this will automatically force the weights to start becoming smaller and smaller. Some of them, like I said, will zero out. So it helps prevent overfitting. So this is the standard technique. If you wanted to see more detail on this, okay, I give you a summary of it. I'll take you to. Okay, if you go to Google. Okay, and search on autoencoder, which we'll be talking about soon. And Stanford. So autoencoder Stanford. If you do a Google on this one. Okay, so you will see autoencoders, deep learning. So this is a very famous handout that people refer to when they are learning autoencoders or. Okay, so I'll talk about autoencoders later, but what I want to. Sorry, that's not the article. The one I wanted to pick is
CS294.
let's see, this is the one, autoencoders and sports. Okay. All right, let me search on autoencoder
Andrew and NG.
Okay, so yeah, so it's called the sparse autoencoder. So the sparse autoencoder. Okay, so anyway, the first part of this handout is standard neural networks, which you guys are experts on, so you don't have to go through this part. Okay, the part that I wanted to show you is the regularization, this equation number 2. So anyway, it's our cost function, as you can see, is m